We will move to next presentation with title Formal and Risk-Based Methods for Designing, Testing and Verifying Autonomous Marine Control Systems. And we will have 4 speakers that will talk. And I would like to invite Professor Asgeir Sørensen to introduce his team and to continue chairing of this session.
Thank you so much. Yeah, we will now have presentation on formal and risk-based methods for designing, testing and verifying autonomous marine control systems. I will give a very short introduction where Mia and Ingrid is supervisors. Before we have a group of 3 PhDs, all as a part of NTNU Amos. That will be Tobias, TORBEN, Thomas JOHANSEN, and Renan G. MAIDANA. I think we, since I'm now also a chairman for the rest, you have to keep your time, guys. So we start just straight on. This presentation can, in a way, be applicable for any marine robotics, but here we have a particular focus towards autonomous ships and ports. And you see this is an emerging era coming up where we are looking for those type of ships for smaller ships, but also the big ships. And of course, there can be different levels of autonomy here. They could be remotely controlled to be more or less fully autonomous. And I think when I first were introduced to this field of autonomous ships, I got a surprise. Normally, we are thinking about automation and maybe also autonomy as a way to reduce manning cost. You're taking out people in daily operations. That's why you are automating. And autonomy is also a way towards that. But by building autonomous ships, bigger ships, you actually could reduce what we call the CAPEX. That is the capital cost, the building cost. Because if you are building a ship where you don't need to have people on board, you don't need that many safety systems, you don't need any support systems, and you could actually maybe also make the steel with less dimension because simply there's less risk on board. So I think this is actually going to change shipping, and also as a part of the green shift, autonomous ships is also one enabler, because maybe one of the biggest contributions to reduce emission is reducing speed. And one reason for having a certain speed is that, of course, you are transporting goods over long distance, but a lot of this can be done slower. And it's simply that it's people on board that is maintaining this higher speed. So I think that is also interesting to look into. We have also been having different projects in Trondheim where these guys are a part of, where we are also teamed up with DNV and Kongsberg Maritime on this. By that, I think I also yesterday introduced different autonomy modules. So we are in this presentation going to look into mission planning, replanning, risk management and supervisory risk control, and also testing verification, integrity of the system. So by that, I think we start with Tobias.
Okay, thank you for the introduction, Asgeir. So I will present some of my PhD work, which is related to verification and testing of autonomous ships. And I will present a recent journal paper that is currently under review, which is about an automated method for testing autonomous ships using Gaussian processes and signal temporal logic. Yeah, so the motivation for looking into verification and testing of autonomous ships is that this has turned out to be a very hard problem, and there's several reasons for this. For instance, they of course have a very high system complexity. They are very complex both in their software and in hardware systems. which means that they can exhibit some very hard to predict emergent behaviors, and even some will use machine learning components. And this means that we really have to use simulation-based methods to be able to assess the system-level behaviors of these ships. And also the operative environment of these ships are characterized by being highly dynamic and structured and uncertain with respect to, for instance, other trafficants and operating in narrow straits with a lot of rocks and so. And this means that the span of possible situations that you can encounter is very large, and you need to run a lot of simulations in order to build enough verification evidence. And thus there's also a need for automation in the testing efforts. And finally, of course, an autonomous ship is highly safety critical. An accident with a ship can be catastrophic. And therefore there is a need for good processes in the specification of the requirements, in the test case selection, and also in the evaluation of the simulations. And also there's need to have some assessment of the verification coverage in order to build sufficient trust. Yeah, so we have developed a method that tries to address some of these needs. So first I will just briefly present the background theory for this. And the first is signal temporal logic. So this is formal logic that we use to specify the requirement that we test against. So an STL formula is built of these so-called predicates, which are just inequalities in this form. And you build formulas by combining predicates with these logical operators and temporal logic operators. So a simple example here is this formula here, which says that you should always keep a minimum distance to other vessels. So this could be read always not distance to vessel I less than a minimum distance. Yeah, so when you evaluate a signal against such a formula, you normally get a true or false result on whether the signal satisfies the formula or not. But using something called the STL robustness metric, you can get a quantitative score on how robustly the signal satisfies the formula. So this is what we will use to evaluate simulations, and we will get out a quantitative number on how well it performed. Yeah, and the other part of background theory that we have used are Gaussian processes. So this is a statistical method for estimating an unknown function, where you start with an a priori distribution, and then you make observations of the function, and can calculate a posterior distribution, which gives you an expected value and an uncertainty for each point on the function. Yeah, so in our case, this unknown function will be the STL robustness score, which I presented earlier. And this will be a function of some scenario parameters. Yeah, so this slide gives an overview of our proposed method. So the input to the method is a test case definition, which is like a scenario with a set of scenario parameters. And also you input an STL requirement to test against. And the main loop of the method goes something like this. The test management system will select a simulation to run, and then it will give a set of scenario parameters to a simulator, which will run this particular simulation and produce a simulation time series as a result. And this is then evaluated against the STL requirement, which gives you an STL robustness score. And this score is then used to update the Gaussian process model, which outputs the expected SQL robustness, and the uncertainty level for the entire parameter space of the scenario. And then this is fed back into the test management system, which uses this information to adaptively choose the next simulation to run. And it uses the expected robustness and uncertainty to do this in a smart way, where it chooses scenarios which either have a low robustness or which have a high uncertainty. And then it will do several iterations of this, and at each iteration it will evaluate a termination criteria. So the testing will terminate either in a falsified state, if it finds a simulation which falsifies the requirements, or it will terminate in a verified state if it finds, if it decides that the test coverage is good enough over the entire parameter space. So this can be stated in an algorithmic form like this, but I won't go into that. So we did a case study to test this method, where we looked at the anti-collision system for a small high-speed vessel. And we developed some requirements, the safety requirement that we saw previous, a mission requirement, which says that you should not deviate from your path more than a given distance. And also we have done an STL version of the call regs, which are the maritime traffic rules. So first we tested in this scenario, which has one scenario parameter. So here you have an incoming obstacle on direct collision course, and the scenario parameter gives the angle from which it's coming. So the goal here is to try to verify that the collision avoidance system can handle incoming vessels from all possible directions. So this shows a run of the testing algorithm again in this scenario against the safety requirement. So you can see here that it terminated in a verified state after 27 simulations. And the reason why it terminated is that you can see this lower confidence bound. This is a 99% confidence interval. And because this is now above 0 over the entire parameter space, we can now say that we are 99% confident that the system satisfies the requirements in this scenario. And here we have a new run against the mission requirement. And here we see that we got a falsification where it found a scenario here with robustness less than 0, which means that it falsified the requirement. So then we can go back and replay what went wrong. So here you see that for incoming ships of this angle here, the control system actually enters into this kind of deadlocked state where it can't get back on its original path. And then we also did a bit more advanced scenario with 2 parameters. So this is a head-on scenario where the parameters are the speed and the avoidance angle of the obstacle. And again, we verified against the safety requirement. So now you can see, since you have 2 parameters, sorry. You now get the robustness surface instead of a curve. And also the number of simulations increases a lot since you now have a bigger scenario space. And this one actually terminated in a falsified state where it found this very sharp peak here, which falsifies the requirement. And we validated this by running a lot of simulations in a dense grid to see how this robustness surface actually looks like. So this is like the ground truth robustness surface. And we can see that actually only 5 simulations in this scenario resulted in a falsification out of 2,500 simulations. It was a very difficult falsifying scenario to find. Yeah, and then we can go back again and look at what went wrong. We can see that it first turns starboard and then tries to go more starboard, and then it sees that it can't go on the outside, and it turned to port, but then the other vessel also turned port and you had a collision. So what's interesting in this scenario is that the region in the parameter space where this happens is so incredibly small. For instance, if we change the avoidance maneuver of the obstacle by just 1 degree, you get a completely different behavior. In this case, it stays true to the call regs for the entire scenario, and you have a completely safe behavior. And similarly, if you go 1 degree in the other direction, then it decides early to break the call regs and go on the inside, and you again have a completely safe encounter. So this very narrow region where we had a collision is sort of when it mixes up these 2 strategies and you get a collision. Yeah, so that's what I wanted to present, and I think this scenario shows that detecting these kinds of emergent behaviors can be very difficult, and you need to run a lot of simulations and you need automation in the testing. And I give the word to Thomas next.
Then I will present a similar topic as what Jens discussed yesterday, but instead of working with small AUVs, we try to do the same with 80-meter long ships. So now it's not just trying to make the ships they're actually dying, but also take into consideration that if they don't behave, then someone else will also have a big problem. So a bit about background. A lot of existing ships, at least a bit more advanced ships, already have DP and autopilots. We have well-defined and well-designed engine control systems. And we have people aboard the ship that selects which controller and which engine to run. But what we then want to do is we want a risk model that can help make these decisions so that we don't need the operators aboard the ship. And our proposed method for doing this is we use a hazard identification method called System Theoretic Process Analysis to find out basically how the controllers in the ship can select ways to control the ship which will lead to a hazard. So if a controller says drive the ship towards land, then you end up at land and you have a big problem. And then we use this SDPA as the basis for making a risk model, similar to what Jens described yesterday. And based on this risk model, we have a supervisory controller, or a switch, that selects what operation mode and what engine mode to use. So then quickly about the STPA analysis. The purpose is to identify how or what can go wrong and how the controller of the ship can actually lead to this happening. And then since this STPA only considers how an accident can happen, we need a bit more information about if something happens, how serious is it? And then based on this, we make a Bayesian Belief Network that gives out a likelihood of an accident. And on top of this, we also include a bit more about how much we expect this accident to actually cost. And then it gives us this big and a bit confusing model. But basically what you see here is we have purple nodes. That's the decisions that the ship can make. We have a lot of green nodes. That's input to the model. And then we have these orange nodes here. That's the way the controller can choose, or that's the way the controller can configure the ship in an unsafe way. So if you choose to operate with autopilot, where you have less control, when you have really low speed inside a harbor, that's typically a bad idea. Or if you select an engine mode that has failed components, that's also not very good. And then at the top here, you have a cost node, where we assume, or we calculate based on the likelihood of different consequences here. We estimate a top cost. That gives us then a expected cost in money of the way the ship is configured now and with the conditions. If we don't change anything, we assume that we have this cost of failure. And then we get a supervisory controller where we choose or use the cost of risk and the cost of operation. And then we can use this to select control modes, machinery modes, set different control objectives. In theory, you should be able to use it to adjust controllers in the ship and also plan the route. And then for each set of decisions, you get a cost of risk and a cost of operation. And then you choose, quite simply, the set of decisions that give the lowest total cost. And then we did a small case study where we have a ship with a DP controller and an autopilot controller. And then we use the risk model with the expected cost of driving the ship to select, should we use DP autopilot? Should we use the main engine as the main driver of propulsion? Should we use diesel generators to provide propulsion? Or should we use diesel generators to provide electricity and the main engine to provide propulsion? And then in the risk model, we get the expected cost of each failure. And then we choose to give a course, or to give to differentiate the consequences in either fatalities, either because you have a limited crew aboard the ship or other ships, you collide with other ships, or here we also think to include some environmental damages, or you get damage to your own ship. And then we choose to optimize the risk versus cost of operation. So different to what Jens did yesterday, we don't set a limit on the risk, because to a certain degree that should be up to the operator or owner of the ship to say, this actually feels worth it. And then we have in this work, we had a simple estimation of the operation cost, where we assume we have this much left to sail, and then we expect to use this much fuel. And we tested for 3 simple cases, where we drove around 27 kilometers, or 14.5 nautical miles. And then in the first, all the machinery system were up and running. The second, the main engine failed after 200 seconds. And in the last, we had a hybrid shaft generator that failed after 200 seconds. And then along the route, which I will show shortly on the map later, we had some conditions around the ship that changed. So then on the first, we had the ship started down here, and then we navigate up to here. And then when we reach this waypoint, it becomes way more challenging because you have more obstacles and ship around the ship. So then the ships, or the controller, lower the speed of the ship to have better control. And then when it's out of this more challenging area, then it increases the speed again before it starts to lower it so that it can stop at the final waypoint. And then here you see also that it changes controller to DP, and then when it increases the speed again, it goes back to autopilot before it chooses DP when it has to stop. And then when the main engine failed, then it switched to a diesel generator mode. And then, yeah, here it lowers the speed a bit slower because now it had lower speed in starting or already, so it wasn't that critical to lower the speed further. Otherwise, it's more or less the same. And then the last was when the shaft generator failed, so that you needed to have the main engine to have propulsion and diesel engines to get electricity. And then it more or less operates similar as with the main engine functioning. And that was most of my presentation. A bit of the further plans on this is to continue to expand the control system. We are now trying to expand it with a map software as well. And we're trying to make a bit more accurate models with the cost. And also try to combine it with what Tobias described in terms of testing, so that we can hopefully, ideally, hopefully we will verify that this is actually a safe way to do it, or if it's not, verify that it's unsafe before we start testing it, because at least I don't want 80-meter long autonomous ships that is not safe for me to be out together with. And with that, I think I will give it over to Renan, and if anyone has some questions, I guess either take it afterwards or just come and ask me later.
Thank you, Thomas. So I'll talk a bit about my PhD work, which is about risk-based decision-making in autonomous systems. So in this slide, I'll just skim through the fact that the point of my PhD project, as far as I know, is to allow autonomous systems to make decisions based on risk assessment. And risk assessment as a formal process is something that happens in the industry by decision makers all the time, as we know. So it's the process of analyzing risk with risk models and then evaluating the level of risk that you calculate against some acceptance criteria. And if your risk is unacceptable, then you have to do something about it. And we know that autonomous systems are able to plan. So AI planning is something that happens and it works. So that's what I'm calling autonomous decision making, is the ability of an autonomous system to make decisions and execute those actions by itself. But in terms of risk assessment, we were looking in the literature about what currently exists in integrating risk assessment as a formal procedure into autonomous systems. And we found some examples of using risk influencing factors, for example, time to collision or closest point of approach in collision avoidance. So for example, one of the works had a ship that was approaching, two ships approaching on a head-on collision, and then the closest point of approach was used with an ant colony optimization algorithm to find out when you should replan. So, but we found no examples as of the time of this review. Sorry. As of the time of this review, we found no examples of integrating formal risk assessment and autonomous operation. So I'll just skim through this because it is an example from a field trip that we made to one of the lakes in Norway. I think it illustrates what we're trying to do here. Jens gave us yesterday some beautiful examples of why you need risk assessment in autonomous operation. So your vehicle might get lost or it might get stuck. And we had some situations in this mission where that a very similar thing happened. But in this case, I was tasked with helping operate this robot here, the otter. We wanted to make some measurements with a hyperspectral camera around this river. But there was no suitable place to launch the boat from here because it's 60 kilograms. It's a two-man operation. So we found this launch pad nearby. So we thought we'll launch the robot from here and then we'll say, go to this point, and then we run over here and take over. This is a picture of the launch pad that I took. You can see it's very tight, so it's not a lot of space to navigate. There are a lot of boats here, and at the time of day that we did this, there was a lot of traffic coming in and out of this marina because it was a summer day in Norway with sun, so people were out in their boats. So some risky situations in this case were deployment and retrieval. So when we launched the boat and when we had to get it back, so it had to autonomously get out of this area and then come back here for us to get it back. Navigation in close quarters, any sort of sensor uncertainty will increase the probability of a collision with those obstacles, and also with collision with other vessels that were navigating here. And this is actually what happened, not a collision, but an encounter with another vessel. So at this point, we were testing some actuators in the boat, and we had completely given up on autonomous operation in this area. We were controlling it manually because we saw it will not work. But when we were doing this, another vessel came and he wanted to park his boat somewhere. So the guy, Christoph, which was operating the boat at the time, he made a decision in his head in like a split second, and then he backed out to this part here. And this means that humans do risk assessment in our heads subconsciously. And I think that's very similar to how robots and AI planning came to be. So it's a cognitive process that humans do subconsciously. And I figured, well, we do risk assessment too, so how can we translate that to a robot? So in this case, if the robot performed risk assessment, it could find out, well, the risk level here is too high, so I need to do something. I can't keep going with my original plan. I have to replan, or I have to stop, or I have to ask for help. So one of the ways that we can do that, this integration, is with Dynamic Probabilistic Risk Assessment. And ADS, the Accident Dynamic Simulator, which I've thought is a terrible name, is a method that's used in nuclear power plants originally. And it works basically by taking the physical system and simulating it in time, similar to what Tobias was saying. But in this case, you have something happens that shouldn't happen, like a deviation from normal operation. And then, for example, in a nuclear reactor, you can have a pressure that's building up, and that shouldn't happen. So at some point, an operator should open a valve or something. And then the simulation here splits into two branches with the probability that the operator did open the valve successfully and the probability that he didn't. And you keep doing this until you have this dense state space of possible accident scenarios. And an accident scenario is when you reach one of those white boxes, which are what we call the end states. So these are consequences. So for example, in this case, it may be that the pressure built up too much and the reactor exploded, which is bad. So the point here is to find all of the white boxes. So you have all of the sequences of events of an accident that can happen to your system in a certain point in time. But you can see this is for a complex system, this is very slow. It's very inefficient to do this. So we thought, okay, let's tackle this problem of inefficiency by drawing upon the basic ADS framework. So it has a planner, scheduler, and simulator. I won't go into detail here. And our framework includes an objective and a post-processing module. And I'll talk a bit about this one later. So we start developing this framework with the simulator, because you have to simulate the state of a system in time. So we wanted to develop the simulator in a modular fashion, because we wanted to see how failures interact and how emergent behavior rises from, for example, injecting a failure in the engine, which is something hard to do when you have a monolithic system model. So we broke down the model, for example, of a ship into energy source, engine, thruster, rudder. And then if you inject a failure in the engine, for example, you can see how that failure propagates to the other parts of the system through the connections here. So that's as far as I got in the work. We're trying to tackle now the problem of efficiency in the simulation. So the dynamic event tree generation, dynamic event tree is what I showed in ADS case for the reactor. It boils down to an infinite tree search problem because that tree doesn't exist. We generate it by simulating. So in the worst case scenario is exponential in time complexity, which is not good. So we have to find a solution with lower time complexity. We ran some experiments to see if that was indeed true, and yes, it validates our analysis that it is exponential. And the other problem is that there is a huge amount of data to be processed after you build the simulation tree. So the post-processing module is responsible for sorting through the data after, assuming that you can compute everything, and then you have to sort it afterwards. So future work is I'm searching the literature, so I'm performing a literature review on DPRA to find solutions to that inefficiency. Then we'll choose one of the solutions or create a new one if we can find any, and finish the development of the framework. Then validate the framework with case studies. So we have some case studies in NTNU that we can use. And then test the framework in a real world autonomous system, such as the Otter. Yeah, and that's basically it. Thank you.
Yeah, we have time for one question. As you see, we try to keep the marine archaeologists without work in the future.